f of x is getting closer and closer to some number L. If that's the case, then we'll call that the limit. Okay? Well, math can't tolerate that ambiguity. That word closer and closer, thanks Angel, as that word closer and closer, that's ambiguous, right? How close do you have to get? Well, on a planetary scale, how close do you get? On a subatomic scale, how close do you have to get? So we need to be much more precise in our words. We're going to do that now. Okay? As a reminder, from here on out, when you see absolute value, it's helpful to think of absolute value as a distance. Okay? So when you see these little absolute value expressions, think of them as distances. All right, so here is the definition. Okay? And I will test you on this. Do you know this definition? It's one of my very few questions where I explicitly say, give me the definition. Most people, it's multiple choice, and most people get it wrong. Okay? Because there is a very precise ordering to this that we want to pay attention to. Okay? It says, for every epsilon greater than 0. Folks, that's the Greek letter epsilon. You can see it written in math print down below. Okay. If for every epsilon greater than 0, there exists a delta greater than 0, and I guess I missed the word if. I said it, didn't write it. If for every epsilon greater than 0, there exists a delta greater than 0. That's that Greek symbol delta. You can see it in math print down below. So that whenever 0 is less than the absolute value of x minus a is less than delta, we have the absolute value of f of x minus L is less than epsilon. This is an extremely complicated definition, folks. So I said I'm going to test you on this definition. I'll put it up as multiple choice. When I put it up as multiple choice, what I do is I scramble all of these expressions. Okay? But there is a very precise sequencing that's happening here. I don't expect you to master this first time through. This is your first exposure to the epsilon-delta definition of a limit. Okay? But, so for right now, I'm looking for regurgitation. Okay? But that in itself is going to be hard enough. Okay? All right. Let's talk about the definition, once you all have it copied. I think of this epsilon greater than 0, I think of it as the tolerance that you're willing to have. Okay? So when we say the y values are getting closer and closer to L, how close do you want the y values to get? You want them to get within epsilon. Okay? Most people think of epsilon as a tiny number. Right? So I figure I'll go ahead and call it the limit if I can get within 0.05 units. Or within 0.001 units of 3. Then I'll call the limit 3. Okay? So think of that as your tolerance. It's the amount of error that you can take. Okay? Well, if no matter what error you're given, you can always find a delta, okay? Which is a corresponding measurement for the x direction, so that as long as the distance between x and a gets within delta, you're guaranteed that the difference between f of x and L is within epsilon. Okay. So let's just put some numbers with this, okay, some abstract numbers. Okay. Let's suppose I want to show that the limit as x approaches a of f of x, in fact, let's say x approaches 2 of f of x is 17. Okay. Well, somebody gives you a tolerance. They say, well, let's let epsilon equal 0.01, meaning as long as you can get within 0.01 of 17, we'll go ahead and call it we'll call 17 the limit. Okay. The question is, how close to 2 do I have to get to be sure that my y is within 0.01 of 17? The answer to that question is the delta. Okay? So if you set delta equal to, and here I'm just making this up because I don't actually have the function, 0.002, as long as my x values get within 0.002 of the number 2, my y values will get within 0.01 of 17. Okay? That's what we're talking about here. That's what I mean by these epsilons and deltas. So epsilon is some tolerance that somebody else requires. Okay? You say, fine, I can get that close to it, provided my x gets this close to A. I said it once before, let me just remind you, think of these absolute values as distances. Okay? So if I want to make sure the distance between f of x and what I think the limit is within epsilon, then I have to get within delta of A. As long as I get within delta of A, then my f of x values will be within epsilon of L. Okay? I said this is a complicated definition. Hopefully you're seeing that. Okay? Hopefully you're seeing there's a very unique sequence to this. Somebody gives you a tolerance. You say, fine, as long as we satisfy this condition, we'll be within our tolerance. Just a second, Mike. The most important word up here, or maybe the most important pair of words up here, are these two. That's what's hard about this. In my example here, I specified a specific epsilon and then was able to give the delta. But I have to be able to do this for any epsilon that somebody gives me. So for sometimes that might be good enough to go ahead and call it the limit. But in other cases, it might be within 1/1,000,000,000th is good enough. Or 1/1,000,000,000,000th is good enough. And for this to be the limit, it has to work for any tolerance that somebody gives you. And that's the hard part of this definition. There's a question.
I'm just trying to keep this straight in my brain. Is this vaguely, is this sort of on the same track as degrees of certainty like in statistics? Like it's basically just a tolerance that you have to be within for the statement to actually be true?
No, not really. I mean, you're all right in fact, I'm using the word tolerance here, yeah. But I've kind of picked that word just to make more sense of the process.
Okay, and that's what I'm
trying
to do.
And with
trying
statistics,
to something that I already know.
Yeah, unfortunately, statistics has a probabilistic statement to it.
Yeah,
and we're not saying if you're within this much, you'll probably be within this much.
This is an absolute certainty.
Yeah, yeah.
Okay.
Good. Great. All right. Folks, you're going to have 2 questions on your next exam related to this section. One will be, can you regurgitate the definition? Okay? Multiple choice. Okay? But I will switch these things around, right? I'll say for every delta greater than 0, there exists an epsilon, which is incorrect. Okay? Or I'll switch these 2 statements around, or something to that effect. So what I'm after is the correct sequencing to this. Okay? So that question will be worth, I don't know, between 2 and 3 points on your next exam. And then there will be one Epsilon-Delta proof that you have to do on the next exam, and I will show you exactly what it is up to the constants that will show up in it. Okay? So this is a tough procedure. I'll let you decide how much of a focus you want to spend on it. Okay? If you can get to where you're able to give the right answer within 2 or 3 hours of study, it's probably worth it. Okay? But if you've spent a couple hours on it and you're not getting anywhere, so this is the most challenging topic we're going to probably talk about in this course. I'm not saying it's the most important or the one that you should spend the most amount of time on. Okay? All right. We're going to try and make sense of it anyway, though. Let's see what we can do. All right. So here, in this diagram, this should make sense. We expect that the limit, as x approaches a of this function f of x, it appears to be what? L. The limit as x approaches a of f of x appears to be L. Okay? Well, let's show what I mean by these epsilon and delta strips here. Okay, so this picture you can find, I would highly recommend looking at the textbook for this section because they've got better diagrams than I can put on the board. Okay? Somebody handed you an epsilon. They gave you, in this case, it's maybe you could argue it's a relatively big one. They say, hey, I'll be happy if you can guarantee that my y values get within this red strip of what we think the limit is. Okay? Well, the question is, where do I have to pick x values so that when I plug the x values into the function, it guarantees that the y values are in the red strip? Okay? So for example, if I pick this x value right here and plugged it into the function, does that put me within my epsilon strip? No. What's the issue? I didn't pick an x value close enough to a to be within that delta strip. Let's pick one closer. How close do I have to go? Well, you can maybe see that if I pick x values within that green strip there, I will be within my epsilon strip. Okay? I have two different distances in this problem. I've got this distance right here between the green strip and A, and this distance right here between the green strip and A. Which one of those two distances is the one that I have to pick for my delta? Go ahead, Zara. The smallest of the two, right? If I take the smallest of the two, then no matter what x value I pick on either side, I'm guaranteed that as long as I pick it within the shortest that distance, I'm guaranteed to be within my red strip here. Okay? So this distance right here is my delta. That's the delta that I'm saying you have to be able to find given a particular tolerance. Okay? So if I go out the delta in the other direction, that's about here. Notice that if I pick any x value from within here, I'm guaranteed to be within this epsilon strip, this range of tolerance that I want to be within. Okay? If I picked one, so here's this distance. If I went out the other way and picked a value and went up, I would not be within the epsilon strip. So that's why I had to pick the smaller of the two for this diagram. Okay? That is one instance. Somebody gave us one particular epsilon. We found one particular delta. That's not the definition. Okay? The definition says for every epsilon. Okay? So let's say somebody else who's a little more careful says, no, no, that's not good enough for me. That's too big of a tolerance. I want you to be within this much of what we think the limit is. Can we still find a delta that will guarantee we'll be within that? Yes. Okay. In this case, our delta is quite a bit smaller. This would be our delta. But we were still able to find it. If I take within delta of either side, I'm guaranteed to be within that epsilon strip. How are we doing? Okay. We could take it one step, so I could just keep going, right? Oops, I should do that in red, excuse me. And here my delta is even tinier. But as long as I pick an x value from within that delta strip, it guarantees that I get a y value within that epsilon strip. Okay. Could I keep doing this procedure? Could I keep doing it no matter how small you make epsilon?
Yeah.
Okay. Then that means that we have found the limit. The limit is L, because you can keep doing this. Okay? So let me give you an example where it breaks down. Let's suppose we look at this function and we mistakenly believe, here's our wrong guess, we mistakenly believe the limit as x approaches a of f of x is equal to L. This is wrong. This is where the definition would break down. Okay? Well, if somebody gave me a really big tolerance, could I guarantee that I can get within that epsilon strip? Yeah. If I set my delta, whichever of these two is smaller, they're about the same. So let's just pick that one. It should be the smaller of the two, but I can't really tell from my picture. As long as I set delta to be this number, if I pick an x value within this delta strip, it guarantees my y value shows up within that epsilon strip. At this point, we're thinking, yeah, there's nothing to say that the limit isn't L. Okay. And even again, somebody else gives us another tolerance, we can still construct that delta strip. But if we go further and further, eventually we will not be able to construct a delta strip. Here there is no delta. For this epsilon. There's no number within A that would guarantee I would get within that epsilon strip. And so that means our guess is wrong. Okay? Folks, your My Math Lab is going to focus on this idea most. Okay? Which is fine. This is where you're going to be developing some intuition. It will give you a specific epsilon. You will be asked to find a specific delta. But it's very important that you understand that's not the whole definition. The whole definition doesn't say, given a specific epsilon, you can find a specific delta. It says for every. The problem is there is no way My Math Lab can test you on the type of problem we're about to do here. Okay? Because it's a computer. It can't judge whether you know something. I don't know if I can do that either, but I can certainly beat it out of a computer. Okay? So, well, let's look at this picture over here. Okay? So that was just for a very simple linear function that we looked at. Here's a more complicated one, so I just want to make sure we understand. Where would our delta be? For this particular problem? Would it be the first point of intersection? I think it would have to be here and here. Because it is true that if I picked maybe this x value right here, I would show up in my delta strip, right? Or my epsilon strip. Okay? If I picked this x value here, yep, I'd end up in it. But what if I picked this x value here? Am I guaranteed to end up in my epsilon strip? No. So how close do I have to go to guarantee it? Oops, somebody's raising their hand. I think I missed it. Thank you, folks. I missed it over here. Where should this be? It should be right here. Thank you. Good catch. Good catch. Okay. This is my delta strip here, and so delta should be whichever of these two is smaller. So that would be my delta, that distance right there. Okay. All right. This is the visual of what we're going to be doing in our proof. This is the visual that goes with it, but you won't see any of this as we do the proof. Okay. So, this is exactly how I will phrase the question on the test, with the exception of, I might say, show that the limit as x approaches 3 of 4x minus 5 is equal to 7. I might even go even further and tell you what the answer is supposed to be, so you know that I know what the answer is, so you don't tell me what the answer is. You do the work that proves that that is the answer. Okay? So this is the type of question I'm talking about. This is worth 5 points on your next test out of 100 points. It is a tough question. Okay? You decide whether you want to ace this question or get a few points on it, or I wouldn't say blow it off, but it's a tough question, folks. But you're only going to get one of them. And so I've had students spend 6 hours studying this question, and they don't study anything else for the test. They get this question right on the test, and then they don't do well on the test. Okay? So, all right. There are 3 parts to answering this question. Okay? One part is usually straightforward, okay? And then students confuse the second and third parts. Okay? So the first part is you need a guess. Okay? So what's our guess? Well, we guess that the limit as x approaches 3 of 4x minus 5. I mean, you would have loved to have seen this question on your last test, right? Give me this limit. Why? Because we can use direct substitution on this. But we're rolling things back. We're pretending we don't have any of those limit properties. Nonetheless, we think that as x gets closer and closer to 3, the y values, we think they should be getting closer and closer to 7. Okay? You may have to do a little bit of work on this. You may not, but you need a guess. Okay? In this problem, if I wrote the directions this way, which I often do for the test, if I wrote the directions this way, you would already have your guess from the get-go. Okay? All right, the next step is the scratch work to find a formula for delta. This part's confusing because when you compare it to the next part, the math work looks very similar. In this part, I am going to assume the conclusion. Does everyone know what I mean when I say assume the conclusion? Yeah, we're going to assume that our answer is right and see what a consequence of that would be. In the next part, we're going to prove that our answer is right. But the work will look very similar. Okay? So, we are going to assume that the absolute value of f of x minus 7 can be made less than epsilon for any given epsilon. This is, if you look at the definition, folks, this was the last part of the definition, right? The part that you have to prove. We're going to assume that we're already less than epsilon and see what a consequence of that would be. Okay? So I'm going to replace f of x with what it is. Well, it's 4x minus 5 minus 7. If this is less than epsilon, what else is true? That's what we're looking at. Okay? Everyone following what I just did there? I took this expression, which was the last line of our definition, and I replaced it with the function. Okay? Well, the 7's right here still. Yep. Good. This gives me, when I do some cleaning up, 4x minus 12 is less than epsilon. Okay? I know where I'm driving this train. I am trying to build the expression. Let me write it up here. I'm trying to build the expression x minus a. We're trying to build this expression. What's our a value in this problem? Careful. A is the limit value, the thing we're approaching. What is x approaching? X is approaching 3. We're trying to prove that f of x is approaching 7. Okay? X is approaching 3. We're trying to prove that f of x is approaching 7. Okay? I'm going to try to write this as x minus 3 somehow. I think I can. I think I could write this as the absolute value of 4 times x minus 3 would be less than epsilon. Okay? And I'm going to run out of room on this problem here, folks. I can now factor a 4. I can pull this 4 out of the absolute value. I'm going to do it this way with an absolute value on it. But of course, what is the absolute value of 4? It is just 4, but sometimes that'll be a negative, so let me leave the absolute value on it for just a second. So then that gives me 4, absolute value of x minus 3 is less than epsilon. I'm trying to build this expression right here. The last thing I have to do is divide this 4 over. So this gives me absolute value of x minus 3 is less than epsilon over 4. This will be my formula for delta when I go through to do the actual proof. Okay. All right, so here, part 3 is the actual proof. Did everyone get that? Does anyone need anything back there? So this is the actual proof. And for this, I have to follow the sequence of things that were given to me in the definition. Okay? So here we go. You do not have to give this to me verbatim. However, it's very easy to give something close to verbatim and be dead wrong. So you might as well just do it verbatim. Okay? So here we go. We're going to let epsilon greater than 0 be given. Somebody just gave me a tolerance for the y direction. What do I have to immediately do? I have to set the distance for the x direction. Okay? So I'm going to set delta, that's not the word set. I'm going to set delta equal to what I found the formula to be over there. So let's just do a quick pause here because this is extremely abstract. If somebody said, I want the tolerance to be within 1 unit of the limit, then I would have to get x to be within 1/4 units of the limiting value. Okay? If somebody said, I want to be within 0.8 of what I think the limit is, then I would just set delta to be 0.2. And as long as x gets within 0.2 of the limiting value, it will guarantee f of x is within 0.8 of that of what we think the limit is. Okay? That's the formula. Now we just have to show that this formula does indeed work. Okay? So that whenever the absolute value of so that whenever 0 is less than the absolute value of x minus 3 and is less than delta, we have, so somebody says what they want their tolerance to be. I say, fine, that's our edge of the delta strip. And as long as we are within the delta strip, what's going to happen? We want to show that we'll be within the epsilon strip. Okay? Well, what is the distance from the limit? It's f of x minus 7. Okay? This part's very important. I am not setting this less than epsilon. I have to prove that this is less than epsilon. Okay? On the previous page here, I mean, my work's going to look very similar, but on the previous page, I assumed we were less than epsilon and then looked at a consequence of that. For this, I'm not assuming that we're less than epsilon. I'm going to prove that we're less than epsilon. Okay? So this would be equal to the absolute value of, I think it was, our function's 4x minus 12. Is that right? No, that's not right. 4x minus 5. Okay? And this work, you should say, hey, this work looks the same, but what's the difference? We haven't assumed our conclusion at this point. Okay? We found a formula for delta. Now we're going to show that that formula actually works. Okay? So this gives me 4x minus 12. Which gives me 4 absolute value x minus 3. There I pulled the 4 out and took its absolute value in one step. Okay. Now, see this expression right here? We did put a condition on it. What did we put as a condition on it? That it was less than delta, right? So the most important symbol that shows up in this problem is right here. This is less than 4 delta. Right? This distance is smaller than delta, so 4 times this distance must be smaller than 4 delta. But what is delta? What did we set delta equal to? We set delta equal to epsilon over 4. So this would be times epsilon over 4. And so really the finesse of the problem is what happens here. Those 4's cancel, and what am I left with? Epsilon. Okay? In the sequence of events, we started with the distance between our y value and what we think the limit is, and we showed that we are less than epsilon. We showed the definition. Okay? Raise your hand if you never want to see that again. All right? Raise your hand if you secretly think that is a little cool. Ah, you don't have to. Go ahead and butter me up. I find that rewarding. I find that extremely rewarding. Okay, this is the first real proof that we've done in this class. Okay? By the way, this is it, right? This is like, you know, there's no more to the story than this. This is how you prove a limit. This is how everyone proves limits. Okay? We started with, hey, a limit means as you get closer and closer, what do the y values do? Then we said, well, let's plug in numbers into a calculator. Okay? Then we said, well, if the function's well behaved, we get a direct substitution property, which makes our life a lot easier. But again, all of that was taken on faith. There's no faith here. We proved it. We proved that this limit, not a very exciting one, but we proved that the limit for this function is 7. Okay. All right, so this is exactly what you have to regurgitate back to me. And if you do so, you get 5 points. Okay. Yeah, just
For a simple function like this where it's not going to be doing anything crazy, is it always going to equal epsilon?
So yeah, that's the finesse of this, right? So we forced it by our choice of delta to come out to be epsilon. How did we force that? Because we assumed our conclusion to begin with. We assumed our conclusion and then looked at a consequence of that, and that's what we chose for our formula for delta. It's not only for this problem, but for all problems that should be the case. Okay? Now, you hit the nail right on the head. This was not too complicated as far as the algebra went. Notice, I mean, you guys might think it's messy, but notice there were no square roots in this particular function we were dealing with, right? Okay? So these can get a lot harder. I will not ask you to go any harder than a linear function. Okay? Kai, yeah.
How did you know what number you could guess, or what could you guess any number for like the very first step where you're setting it equal to 7?
Oh yeah. So there you do use so that's kind of a silly thing, right? In math, you usually don't prove something unless you already know the answer to it. So yeah, when I guessed this, I did the direct substitution property. Go ahead and plug in a 3, and you get 7.
Okay.
So, or you could use a calculator and plug in tiny numbers, and you'd get 6.999, and you say, I think the answer's 7. But now we've actually proved it. Okay? This is how we know that the answer's 7 and not 6.99999 or something like that. Okay? Mike?
So when we do our assumption and then we go to our proof and then we prove that it is not in fact true, have we basically proved that it's not true? Like
No.
It does not equal epsilon?
Right. So if I say for any needle in the haystack, you can find an appropriate delta. If you can't find a delta, that doesn't mean the limit isn't that.
So we need to go back and change our assumption as opposed to
well,
just
so it may be that the limit doesn't exist, and we're not going to go into how you prove a limit doesn't exist, with the exception of you could find an epsilon and show that there's no way you could get within that epsilon strip, but that's a case-by-case basis. Yeah, we're not going to prove a limit doesn't exist in this. It's too hard. Mike?
So,
Michael.
like the third, oh, that's good. On the third or fourth to the last step.
Of the part 3?
Yeah, part
Uh-huh.
3.
Yeah.
Do we just assume that the x minus 3 is delta because we've already said that answer is going to always be the one that's less than delta?
Well, so we've said that x minus 3 is less than delta, and that's what I wrote. This is why this ordering is very important. So I said so that whenever this is the case, what do we get? And here I am saying x minus 3 is less than delta. When do I use that fact? That fact creeps up right here. When I replace x minus 3 with a delta, and I get to change this to a less than symbol, which is kind of the most important symbol that shows up through this procedure.
And it'll always be like a less than symbol, right?
Yes, because we're saying, so if you go back to the idea of these strips, we're saying, hey, if I want to guarantee that the distance between the y values and L is less than this amount, I have to pick x values that are less than this amount. Yeah. So let's put a picture with this. I ask you to draw the epsilon for this limit. So let's see, this is the limit for the function 4x minus 5. So the graph of this function looks something like this. Here's negative 5, and we've got a slope of 4. So we're rising fairly steeply. Here's f of x. We said that at x equals 3, we expect the limit to be 7. Okay. So here, I mean, this is just a sketch, but I'm actually going to try to be sort of careful with this. If this was 7 plus my tolerance, there's my epsilon strip. And this would be 7 minus my tolerance. Okay. I'm trying to be kind of careful with this picture, actually. In relation to epsilon, how big does delta have to be? Yeah. In relation to epsilon, how big does delta have to be? Smaller. In some cases, in this case, yes, but we can say precisely how much smaller it has to be. Will? No?
Well, it's smaller by the ratio between L.
The delta has to be a quarter the size of the epsilon. If this is epsilon, and I take a quarter of that, that will give me my delta strip. This distance right here is my delta, which is equal to 1/4 of the epsilon amount. Yeah?
And is it safe to say that that behavior is because the slope of the graph there is approximately...
The slope of the graph is 4. Yes, it is. There's a relationship between the choice of delta and the slope if you're dealing with a linear function. But that's only for a linear function. But all the others are so much more difficult to work with.
Are those F's or 7s?
Those are 7s. Sorry about that. Yeah, that's hard to see. That in this case, the limit is 7. And so that's the y value that we put up there. Thanks, Angel. No, thank you. Okay. Tough stuff, folks. All right. I don't have time. I wish I could now say, all right, folks, I'm going to let you practice this exact same problem 2 or 3 more times where I just change up these numbers. Okay? You have to do that. Okay? If you look at the review for the last unit, I have put 2. If you look at the last unit, the Unit 1 review, I've put 2 epsilon problems on there. And you can practice those, and you've got my worked out solutions to them. Okay? If I get a chance, I'll make a video where I just do this one more time with brand new numbers. Okay? But I don't know if I'll get to that soon. Okay? So please, if you want to master this problem, you got to do it 2 or 3 more times with new numbers and see the pattern. Okay? Something that's very important is that you follow this sequence of guess, scratch work, and then answer. What you do for the guess or scratch work is sort of up to you, but when you come to the proof part, this sequence is incredibly important. And if you interchange these sentences, what you're saying isn't what it doesn't make sense. All right, let's do one more. Epsilon-Delta proof. Okay, this one is a little bit too hard. It's not significantly harder than the last one. Okay, but there's more algebra going on, and so I'm not concerned with you replicating this. But let's see if we can get the procedure down. Okay, so step 1, what do we need?
Yes.
A guess. So for this, I'm just going to use all of my early limit tools that we've already developed. So let's look at the limit as x approaches negative 3/2 of 9 minus 4x squared all over 3 plus 2x. Well, that would be the limit as x approaches negative 3/2 of 3 plus 2x times 3 minus 2x all over 3 plus 2x. Okay, so this problem should seem like very much like a Unit 1 problem up to this point. Now I can use, so again, this is a guess, so I'm going to go ahead and use that direct substitution property. We get 6. How else could you come up with your guess? Well, since this is just a guess, you could use a calculator to check. Okay. As you plug in numbers getting closer and closer to negative 3/2, what are your y values getting closer and closer to? 6. Okay, so that part's just coming up with a guess. All right, let you get caught up. Okay, the next thing I do is scratch work. Yeah, so I'm going to start off assuming, so this is important, I'm assuming my conclusion. I'm going to assume that the absolute value of f of x, that's an f there, minus 6 is less than some given epsilon. The assumption part is I'm assuming that it's already small enough. Then we're going to see what a consequence of that will be. So that gives us the absolute value of 9 minus 4x squared all over, what is our denominator? 3 plus 2x, thank you. Minus 6. If this is less than epsilon, then what do we end up with? Well, and again, I'm going to run out of room on this. We would just have 3 minus 2x minus 6 after we do the canceling. So I've got factor and cancel. That's what we'd be left with. Which would give us negative 3 minus 2x is less than epsilon. And remember what I'm trying to build. I'm trying to build absolute value of x minus a. So let's factor out a 2 from this. 2 doesn't go into it. Well, we can still divide 2 out of both terms. So I factor out a 2. Actually, I'm going to factor out a minus 2, so it gives us negative 2 times positive 3/2 plus x is less than epsilon. So if I lost you there, distribute that negative 2 back through and see that we have the line above it. I'm now going to pull that negative 2 out of the absolute value. I'm going to do it in 2 steps. This will give me negative 2 absolute value times the absolute value of x plus 3/2. I just did a reordering there. Is less than epsilon. What is the absolute value of negative 2? Why, it's 2. And I'm going to rewrite this as x minus negative 3/2. Why did I write it as minus a negative? I'm trying to put it in the format x minus a. So lastly, we see that this gives us the absolute value of x minus negative 3/2 would be less than epsilon over 2. All of that work is bogus work. How come? Why does it not hold for a proof? We assumed that the answer was correct. We assumed our conclusion, right? So that's going to be our formula for delta. Okay? For those of you that go on to take more math classes, okay, eventually you'll get to math classes that are just riddled with Epsilon-Delta proofs. You look at an advanced calculus class textbook, and it is all just epsilon-delta proofs. Okay? Unfortunately, the authors will never show you this scratch work. You'll be reading along, and he'll say, now set delta equal to epsilon over 7. And you'll say, where on earth did that come from? It came from the scratch work that the author was doing. So now let's actually do the proof. Okay? You can deviate from this script, folks, but it's easy to go wrong if you do. Okay? So how does it work? We say let epsilon greater than 0 be given. What do we immediately do? We turn around and we set delta equal to epsilon over 2. Where did that choice of epsilon over 2 come from? From our scratch work. So that whenever 0 is less than the absolute value of x minus a is less than delta, we have the absolute value of f of x minus 6, that's what we're claiming the limit is. And what's our goal here?
Shouldn't be the absolute value of x minus.
Yeah, let me go, yes, you're exactly right. I should go ahead and plug in the value there. So that'd be x minus what?
3.
I think we're approaching
Oh, I'm sorry.
negative 3 halves in this one. Thank you, good catch.
Would it be okay to do that parenthesis there because you have two?
Of course, yep. And in fact, I only didn't because I don't have a, yeah. Good.
And why is it important that we write it as minus 3 halves instead of plus 3 halves? Or minus
You,
negative 3
well,
halves?
so you could put plus 3 halves, but the issue is what is x approaching in this problem? X is approaching minus 3 halves. So we always like to write it as x minus a, the distance between x and a. Yeah. So you could write it that way, provided you're thinking of it as minus a negative 3 halves. Great. Yeah.
Yeah.
Okay. So what's my goal? My goal is to take this expression right here, and if you're looking at the limit definition of the derivative, excuse me, if you're looking at the epsilon delta definition of the limit, we've basically given that definition for this problem, and our goal is to show that this is less than epsilon. Okay, so here we go. This gives us the absolute value of 9 minus 4x squared all over 3 plus 2x, thank you, minus 6. And now this part should seem like something we've already done. And it is, except we haven't assumed our conclusion yet. So this would give us the absolute value of 3 minus 2x minus 6, which gives us the absolute value of negative 2 times absolute value of 3 halves plus x, which gives us 2 absolute value of x minus negative 3 halves. And here it is. What did we say? I mean, we didn't assume our conclusion. We assumed the preamble of the definition, the first part of the definition, that this is less than delta. This expression right here is less than delta. Provided we get within delta of our a value, what do we get to say? Well, so this distance here would be, oops, and the most important symbol, this one right here, this is less than 2 delta. But what was delta? What did we set delta equal to?
Delta halves.
Epsilon halves.
Or epsilon.
Yep, that's right. Epsilon over 2. What happens? There's the finesse. Okay? We just showed that we got within epsilon. Give yourselves a pat on the back. You know. In fact, we can do one better than that. Rather than the pat on the back, go ahead and draw a little box here and then fill it in. That's what math people do when they finish a proof. I don't know why. It means you're done with the proof, and usually it also means you, the reader, probably won't see what just happened. Go figure it out.
And the last two symbols are equals instead of less than?
Yes.
Okay.
Yeah, but remember, it's one string, so this is still less than this,
Okay.
even though these last two are equals. Yeah. Okay. Fun stuff. That one's a little bit harder, not because of the procedure, but because of the algebra involved in coming up with our epsilon. And in general, the more complicated the function, the harder it is to come up with a formula for epsilon. Okay? So that's why I'm just keeping you at the, I've said, for you guys, you just have to do this linear one right here, but with different numbers. Okay? All right. So again, let's just summarize the process. 1, you need a guess. You can use any means necessary for that guess. Usually, just the tricks that we taught in this class. Okay. By the way, that last one was a lot more interesting. This last limit was a lot more interesting. Why? Because it was an indeterminate form, as opposed to a line where you knew what the y value was supposed to be on a line. Okay. But anyway, you can use any means necessary to come up with a guess of what you think the limit is. Okay. If you guess wrong, you won't be able to prove it. Okay. So the next step is your scratch work. And the key part to that is that you go ahead and you assume that the absolute value of f of x minus L is less than epsilon. And then you find a formula for delta. Okay. Part 3 is your proof. This is what matters. Okay. And you're showing that your formula works. Okay. So that's the general procedure for doing this. Yeah. Whose side? Yeah. That's tough stuff, folks. Okay? All of calculus can be built on these epsilon-delta proofs. Okay? You should go through and prove every single thing we've done in this class using epsilon-deltas. Don't do it, okay? But you should, I mean, that's the idea, right? Anything I've said, take this on faith, you can actually do with an epsilon-delta proof, okay? So for example, one of the most common limit properties we've used in this class is the sum property, and I'm going to prove that here in just a second using epsilons and deltas. Okay? But let's first, before we can do that, I need to give you the triangle inequality. It says that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Arguably one of the most important properties in math. Shows up in the darndest of places. Okay? What was that? Doesn't look that important. Yeah, it's not really that impressive. But you can use it when you least expect it, which is kind of nice. Okay? Let's see pictorially what we're saying here. Okay? Why is it called the triangle inequality? Well, let's say I have this side of a triangle. Let's label it A. That's the length of it. Okay? And I have another side of the triangle going off this way. Let's label it B. Okay? Well, I could now form the third side of that triangle, and I would call this length A plus B. Okay? And there was a property, go back to some Greek, that said the sum of any two sides of a triangle is always longer than the third, or always at least as long as the third. How long is this third side right here? It's this distance. This third side is less than or equal to the sum of these two sides to the triangle. Yes, it can be equal to, in the one instance where if I took this triangle and folded it down, like, could you picture this? If these 2 points were hinged, I pull this down here, then they would actually be equal to each other. If they're so nobody would think of this as a triangle. Here's one side, here's the other, there's the third, but in that case you'd have equality. Okay. So let's just see how this works. If I gave you the absolute value of 3 plus negative 1, the triangle inequality says this is less than or equal to the absolute value of 3 plus the absolute value of negative 1, right? Because what's this right here? That's the absolute value of 2, which is certainly less than or equal to 3 plus 1, because 2 is less than or equal to 4. So there's how you can use the triangle inequality with just values. So this is the property, this is an example, and this is a pictorial proof. All right, so we're going to need that. We'll skip this one. This one's a doozy, folks. Even where we could use direct substitution, proving that limit is tough. Okay, I'm going to skip it because I don't have time, and I'm definitely not going to hold you responsible for it. Okay. All right, so let's look at the proof of the sum law. So recall that the sum law said this. It said, suppose we know two limits. Suppose we know the limit as x approaches a of f of x is equal to m, and the limit as x approaches a of g of x is equal to n. Then what did the sum law say? It said, hey, if you want to take the limit of the sum of those two functions, the limit would just be m plus n. You can distribute limits over sums. Okay. You guys have already gotten a lot more careful at reading. Let's just highlight something that you might have missed on our first pass. This sum law, can I distribute limits over any sums? Well, provided the underlying limits exist. That's what we assumed to begin with. Then we said you could go ahead and distribute. If one of these limits didn't exist or was infinity, you can't use the sum law. Okay. All right. So let's prove this. Okay. Well, let's see here. Let me might have to do a little scratch work first. Yeah, let's do it like this. Let's follow my order. So one, we need a guess. Well, that's exactly what we're asked to show, that the limit as, you don't have to write this part down, it's kind of redundant if you don't want to. But our guess is that the limit's going to be what? M plus n. Okay. Then let's go ahead and assume our conclusion. Suppose that the absolute value of f of x plus g of x minus what we say the limit is, suppose this is less than epsilon. Okay. So let's see where we're trying to go with this proof. We know a couple things. We know this fact, and we know this fact. Let's see if we can make use of them somehow. Okay? So what I'd like to do is let's go ahead and take this expression right here and regroup it like this. Yeah. Yes, thank you. Good catch, Victoria. That should be an absolute value there. Thank you. What am I at? 28? Okay. All right. I have the absolute value of the sum of two quantities. I'd somehow like to break this up into smaller portions. What can I use? Yeah, the triangle inequality. Here I've got the absolute value of the sum of two things. this is less than or equal to the absolute value of the first plus the absolute value of the second. Okay? Well, now this is so after you've proven a limit, or after you know a limit exists, you're armed with some pretty powerful information. I know that I can always make this smaller than any number I want, because the limit exists here. And I know I can always make this expression smaller than any number I want. Let's make this this expression right here, let's make it smaller than, here's the trick, epsilon over 2. We can make the absolute value of f of x minus m, we can make this smaller than epsilon over 2 for some delta 1. I don't know what the delta is, but I know it has to exist. Why? Because the limit exists, and it says for any epsilon we can find a delta. So for epsilon over 2, we'll find a specific delta. And we know that for g of x minus n, we know that this quantity here can be made as small as we want. Let's make it smaller than epsilon over 2.
Why epsilon over 2?
Yeah, great question. Because eventually I'll add the two together, and the finesse will be to make it epsilon.
Okay.
Yep. And this is one of those things that I wouldn't expect to do. I wouldn't expect you to know it until I showed it to you. Yeah. For some delta 2. So as long as this expression gets small, or sorry, as long as x minus a gets smaller than delta 1, I can make this expression here smaller than epsilon over 2. And as long as x minus a gets smaller than delta 2, I can make this expression smaller than epsilon over 2. So my formula for delta, we're going to take the minimum of these two deltas. Okay? Because let's just say delta 1 is a smaller number than delta 2. Then if I set delta equal to delta 1, then this will be true and this will be true. Because you can always go with a smaller delta. If one delta works, so will any delta smaller than that. Okay? So here's the proof. Let epsilon greater than 0 be given. Set delta equal to the minimum of delta 1 and delta 2. So that whenever 0 is less than the absolute value of x minus a is less than delta, we have. So folks, I know, first of all, I'm not going to test you on this. I think it's important for me to show you one of these can be proven using the epsilon delta definition. Okay? But the other thing is even though I'm not going to test you over this one, the procedure should start to seem a little familiar. We start with a guess. We find a formula for delta. That's a lot harder in this case. It requires a lot more intuition than just working through things mechanically. And then part 3 is the proof. And look, I'm writing out the exact same thing here for the proof. The only way these problems get different is what algebra do I need and what formula do I pick for delta. We have the absolute value of f of x plus g of x minus parentheses m plus n. Okay, so now I'm not assuming this is less than epsilon. But this can be rewritten as absolute value of f of x minus m plus g of x minus n. I'm stuck. I want to break up an inequality. What do I use? sorry, I want to break up an absolute value. What do I want to use? The triangle inequality. It's a nice way to break up an absolute value. Okay? But then that gives me a less than or equal to, not equal to. So this is less than or equal to the absolute value of f of x minus m plus absolute value of g of x minus n. But this can be made less than epsilon over 2, provided we're at least as small as delta 1. And this can be made less than or equal to delta 2, or made less than or equal to epsilon over 2, provided we're less than delta 2. And we made our delta with smaller of those two numbers, so we're guaranteed to be within that. And what do we get when we add epsilon over 2 plus epsilon over 2?
Epsilon over 2.
We get epsilon. And I've made a mistake here, folks. 29, that should be a less than. Not going to hold you responsible for this problem right here. Okay? But I did want to show you that everything we've done in this class could be built up from scratch using these epsilon delta definitions. Why don't we do it? Because if I started off the first day of class with an epsilon delta definition, the next day I'd have one person or two people left in class. Plus we'd never get anywhere. It takes a long, long time. Okay? That's our epsilon delta definition. That's all there is. I'm not hiding anything from you at this point. I'm not saying let's simplify it so you guys can feel good about it. This is as complicated as it gets, which is kind of cool. By the way, it took years, it took centuries to develop this idea. People argued over what do we mean by this notion of a limit. It was first proposed by the Greeks. But it wasn't until, I'm not quite sure when. Calculus was developed by Newton and Leibniz, but even still, it was sort of left as kind of these fuzzy ideas, and it wasn't until a little while later that we got very precise with these epsilon delta definitions. Okay. It took over 1,000 years, maybe 2,000 years to develop this idea to what you see here. Okay. So you have an hour and 10 minutes to learn it. Okay. All right. One more. Okay. First of all, please note I made a change to this. This probably won't agree with your notes, unless you just printed them off this morning. It should be 1 over x squared there, not 1 over x. Okay. So I now want to define what we mean by having an infinite limit value, or having the limit be infinity. Okay. It's still going to have a delta involved, but there's no epsilon here. Epsilon usually stands for a small quantity. Instead, we're going to have an m. This capital M usually stands for a big quantity. Okay? So we'll just do this real fast. Let f be any function. For any number m, and you usually want to think of m as a big number, like 1,000,000. If for any number m, there exists a delta, so that as long as you get within delta of your limit value, you can make the y value bigger than that m, then we can say the limit's infinity there. This actually goes back to when you were little kids on the playground and you were talking about the idea of infinity, right? And somebody say, well, how big is it? Well, think of a number. It's bigger than that. Think of another number. It's bigger than that. This says no matter what big number you pick, you can make the y values bigger than that number. If that's the case, then we say that the limit is infinity.
Would it be misleading to think of m as just inverse epsilon?
There's a relationship there. Yeah, it's not misleading. There's a relationship there between the quantity m and 1 over that quantity being small. And we'll see that when we do the proof. But it's not quite the same because our y values are not approaching something. They're getting beyond something here. So it's a different idea, but you're right. There's going to be an inverse relationship between our delta and our m. All right, so let's prove this. All right, so one, we need a guess. Well, that's easy. The limit as x approaches 0 of 1 over x squared, what's our guess? That it can be made arbitrarily large. Okay? 2, let's come up with a formula for delta. Okay? This one's not, this isn't going to be quite as precise, and I'm not going to ask you to prove these. Okay? For any m greater than 0, we want a delta greater than 0 so that we can make the absolute value of 1 over x squared bigger than m. Okay? So what I'm saying here is give me a big number like 1 billion. I can show you that I can make this expression bigger than 1 billion, provided we get this close to our limit value. Okay? Provided 0 is less than absolute value of x minus 0 is less than delta. So folks, here our a value is 0, so sometimes I might just write absolute value of x rather than x minus 0. Okay? Well, suppose we get what we want. Suppose that 1 over x squared, I don't need the absolute value because that's positive, is bigger than m. What else would be true? Well, if that were the case, then we'd have that 1 is greater than m times x squared, or we'd have that 1 over m is bigger than x squared. Doing a little algebra there. I can do all this kind of carelessly with the inequalities because all these quantities are positive. Okay. Which would mean that, again, only because all these quantities are positive, that the square root of 1 over m would be greater than absolute value of x. Which would mean that the absolute value of x would have to be less than 1 over the square root of m. But I could think of that as the absolute value of x minus 0 has to be less than 1 over the square root of m, and this is our formula for delta. Any questions? Desiree, how are we doing? Any questions? Yeah.
It just looks like a smiley face.
Where? This?
Yeah.
Sorry, that's an arrow. It's an arrow. Yeah. Have fun with this problem. That's an arrow in each of those cases. Great question. Okay. All right. So here's our proof. Okay. Let m be given. Somebody gives you a big quantity. You're going to set your delta equal to 1 over the square root of m. If m is a big quantity, what is 1 over the square root of m? It's a very small quantity, right? Which is sort of what you would expect. Okay. So that whenever the 0 is less than the absolute value of x minus 0, which is less than that delta, we get the absolute value of 1 over x squared. Sorry, this one works out a little bit differently. So we know that the absolute value of x then is less than delta, which means that if we invert this, we'd have 1 over the absolute value of x would be greater than 1 over delta. And then we could take 1 over the absolute value of x times 1 over the absolute value of x is greater than 1 over delta times 1 over delta. Okay. I might lose you on that step. If this is true, then I could, and they're all positive, then I can square both sides, which is essentially what I'm doing here. So we get 1 over the absolute value of x squared is greater than 1 over delta squared. But now I don't need the absolute value on this side. So we have 1 over x squared is greater than 1 over delta squared. But what is delta? It's 1 over the square root of m squared. But this is the same thing as 1 over m, which is the same thing as m. So what did we just show? The y value is greater than that fixed number.
Can you go back up?
Yeah, of course. I did that really, really fast.
How can you flip the sign?
Yeah, that's a great question. So there's a property that says if 0 is less than a is less than b, then 1 over a is greater than 1 over b. So for example, if 0 is less than 3, which is less than 5, if I invert 1/3, how does 1/3 compare to 1/5? 1/3 is bigger than 1/5. So when you have two positive quantities and you invert them, it changes the order of the inequality. Yeah, that's a great question. That was taught to you in about 10 seconds in a college algebra course, and here it is coming back to you. What's that?
Let's not forget that.
Yeah, don't forget that important detail. It's like watching The Wire or something. You gotta pay attention to every single little detail or you'll miss something. All right. Let me just show you pictorially what we just did. Here's the graph of 1 over x squared, right? So say somebody gives you some threshold value, m. They want you to guarantee, or they want you to say, can I make the y values of this function bigger than m? Sure, provided you get within 1 over the square root of m. If you get within 1 over the square root of m and plug it into the function, it'll spit out a y value that's bigger than that m. That's what we just showed. Okay. So let's actually put some concrete numbers to that. For example, can you find a delta so that 1 over x squared is bigger than 1,000,000? As long as the absolute value of x minus 0 is less than that delta. That's what we're saying here. And the answer is sure. Set delta equal to 1 over the square root of 1,000,000. That is, set delta equal to 1 over 1,000, or 0.001. As long as we get x values within 0.001 of 0, then our y values will be bigger than 1,000,000. What if we want to be bigger than 1,000,000,000? Then just do 1 over the square root of 1,000,000,000. What if we want to be bigger than 1,000,000,000,000? Then do 1 over the square root of 1,000,000,000,000. Regardless of what threshold somebody gave us, we have a formula for how close we have to get. Because that formula will always be available to us, then we can say that the limit is infinity. Okay? Boy, 2 days in a row. All right, folks. 1, today's lecture was tough. Okay. 2, I've made it very clear what things I'll test you on from this lecture. Okay. That is the limit definition of the epsilon delta definition of the limit, and I'll have you use that epsilon delta definition to prove the limit for a linear function, like that first example. Okay.